So I'm going to do a couple of examples of calculating derivatives, including logarithms, but I also wanted to start by an alternate way of calculating the derivative of the log base a. And so the previous video, what we did was we calculated the log base a in general, and then said, well, if the base is e, then the derivative of the natural logarithm is this thing. And so I'm going to go the other direction and start with the specific case where you're doing base e, and then use that to get the general case. So let's actually start with the natural log, which is base e. Okay, and we're going to do the same thing that we did before, which is we're going to convert this into the inverse relationship. So if I have y is equal to the natural log of x, this is equivalent to saying that e to the y equals x. And then I'm going to differentiate it implicitly. And so remember, we need to use the chain rule because y is a function of x here. So the derivative of e to the y is itself, so it's e to the y, but then I also have to multiply by the derivative of y with respect to x. That's the derivative of the left-hand side. The derivative of the right-hand side is 1. And so then we have dy dx is equal to 1 over e to the y, and 1 over e to the y is the same as 1 over x, because e to the y was x. So that gives us the derivative of the natural log. And then if I want to calculate the derivative of the of a general log base a, we use the change of base formula. So if I want to calculate the derivative of log base a of x, that's the same as the derivative of log base a of x is the same as the natural log of x divided by the natural log of a. And when we do that, keep in mind that the natural log of a is a constant. Okay, so this is the same thing as 1 over the natural log of a times the derivative of the natural log of x. So it's 1 over the natural log of a times 1 over x, or 1 over x times the natural log of a. Okay, so this is another way of calculating that, starting with the specific base of base e, and then using the change of base formula to do any base a log. All right, so let's take a look at a couple of examples. So here's an example. We're going to differentiate log base 10 of 2 plus sine of x. We are going to use the chain rule here because we have a composition of functions. We have 2 plus sine of x used as the input to the log base 10. So f prime of x is going to be, well, the derivative of log base 10 says I take 1 over the input times the natural log of 10. And then I have to multiply by the derivative of that input. This is the chain rule. Okay? And that input is going to be 2 plus sine x. So the derivative f prime of x is going to be the derivative of 2 plus sine x. Well, the derivative of 2 is 0, and the derivative of sine x is cosine of x. So I'm just going to take that cosine of x, which is the derivative of 2 plus sine x, and I'm going to put that in the numerator. So this is cosine of x divided by 2 plus sine x times the natural log of 10. Okay, let's take a look at another example. So here we're going to find the derivative of the natural log of this function x plus 1 divided by square root of x minus 2. So we might first think that we're going to use the chain rule again, and inside that chain rule we're going to use maybe a quotient rule. Okay, so let's do this again by chain rule. So the derivative of this stuff, natural log of x minus 1 divided by square root of x minus 2 is, I start with the reciprocal of that input, and then I'm going to do times the derivative of that input, where that input is x minus 1 divided by the square root of x minus 2. And I actually, sorry, it's x plus 1. And when I put this into taking the derivative, I actually am going to write that square root as a power 1/2, just to remind myself that I'm going to use the power rule there. Okay. So now when I do this, I have this reciprocal of this fraction is, I'm just going to flip it. So it's the square root of x minus 2 divided by x plus 1 times, now I need to use the quotient rule here. Okay, so bottom times the derivative of the top. So this is going to be square root of x minus 2 times the derivative of x plus 1 minus the top x plus 1 times the derivative of x minus 2 to the 1/2 minus the top times the derivative of the bottom all over the bottom squared. So I'm just going to rewrite that as x minus square root of x minus 2 squared. Okay, so this is now square root of x minus 2 divided by x plus 1 times square root of x minus 2. Derivative of x plus 1 is 1 minus x plus 1 times the derivative of x minus 2 to the 1/2 is 1/2 times x minus 2 to the negative 1/2 times the derivative of the inside and then all over, that's going to be x minus 2. Okay, so this now becomes square root of x minus 2 divided by x plus 1 times square root of x minus 2 minus, let's see, I'm going to put this over x minus 2 minus x plus 1 divided by, the reason I did that is so that I could actually use this negative exponent. There's a 2 in the denominator. I have the x minus 2 that was already in the denominator, and then I have a square root of x minus 2. And then times the derivative of x minus 2, well, that's 1. All right, there's a little bit of simplifying that I can do here. I can do, let's see, I can multiply this through. So square root of x minus 2 times the square root of x minus 2 is x minus 2 divided by, we have x plus 1 times x minus 2 minus, I have square root of x minus 2 times x plus 1 over 2 times x minus 2 times the square root of x minus 2. We have some factors that cancel here. And it looks like we get 1 over x plus 1 minus x plus 1 divided by 2 times x minus 2. I'm a little bit surprised that there's no square roots left. Anyhow, this was supposed to be the derivative of the natural log of x plus 1 divided by the square root of x minus 2. Now, some of you might have noticed, natural log, or like the logarithms, when you have stuff put into the logarithm, logarithms do funny things with quotients. And so if you remember some properties of logarithms, logarithms turn multiplication into addition, and they turn division into subtraction. And also they turn powers into multiplication by a constant. So there's the fact that a log with any base of a product of two numbers is equal to the log of the sum of the logs. The log of a product is the sum of the logs. And also the log of any power is, you bring that power out as a multiplier times the log. So in fact, and so just like the log of a product is the sum of the logs, the log of a quotient is going to be the difference of the logs. So another way to do this is we can take the derivative of the natural log of x plus 1 divided by square root of x minus 2. And this becomes the derivative of the natural log of x plus 1 minus the natural log of, this is x minus 2 to the 1/2 power, right? Which is now the derivative of natural log of x plus 1 minus 1/2 times the natural log of x minus 2. Okay? Now, when I take the derivative of the natural log of x plus 1 is 1 over x plus 1 times the derivative of the inside. The derivative of that inside function is 1. Minus 1/2 times the derivative of natural log of x minus 2 is 1 over x minus 2 times the derivative of that inside function, which is again 1. So this is equal to 1 over x plus 1 minus 1 over 2 times x minus 2. For some reason, this is not the same as what we got before, and I am not sure why. I don't know if I'm going to leave this mistake in the video or what. Let me see if I can find the mistake. And I will say, one thing to notice is, the quotient rule has a lot more to keep track of, which is why this is one of the things that we really love about logarithms. Logarithms change products into sums and quotients into differences and exponents into scalar multiples. And the thing is sums and differences are much easier to deal with in differentiation than quotients and products, right? The derivative of a sum is the sum of derivatives, where the derivative of a product, you have to mess around with the product rule. And messing around with the quotient rule, that's a pretty messy rule. Okay, so it's much easier to just take the derivative of a difference than it is to take the derivative of a quotient. So this is one of the beautiful things that we do with natural logs. And this forms the basis of our logarithmic differentiation, which I'm going to do next. So let me take a look and see if I can find the mistake. Let's see. Where would the mistake be? So I took 1 over that function times the derivative of the function. 1 over that function is the same as the reciprocal of the function. Now the derivative, I take the bottom times the derivative of the top, yes, minus the top times the derivative of the bottom, all over the bottom squared. Okay, so I have this piece is just rewritten. Square root of x minus 2 times 1 x plus 1 times 1/2 x minus 2 to the negative 1/2 power times the derivative of the inside. Okay, and here I separated these out into terms. Square root of x minus 2 divided by x minus 2 minus, this is x plus 1. And I pulled this down, so there's the 2 is downstairs, and the square root of x minus 2 is downstairs, times 1. 1 is the derivative of x minus 2. Okay, and now I distributed this factor on the outside to both pieces. Square root of x minus 2 times the square root of x minus 2 is just x minus 2. So x minus 2 in the numerator, x plus 1 times x minus 2 in the denominator. And here I have square root of x minus 2 times x plus 1 divided by, there is a mistake. When I multiplied this factor times this term, there was that piece times x plus 1 there. Okay. And that should have canceled. And this would have been just a 1 in the numerator. Okay, found my mistake. And there we go. So we got the same answer in both cases. 1 over x plus 1 minus 1 over 2 times x minus 2. And I would say that doing it by using the logarithms to convert the quotient into a difference made it a much easier process and much less work to keep track of. Okay, wonderful. So next time we will look at logarithmic differentiation.